Can you hear me okay? Okay. All right. So yeah, Randy is correct. I'm on several ASHRAE committees. I'm on 189 high performance, on the energy and water technical committees, as well as the standard 191, which is a water efficiency for buildings. It's not out yet. Hopefully this year we'll get it out for publication. So, but today's focus will be water saving technologies. And some of the learning objectives. I'm going to step back here. Drought conditions in the United States. Probably aware of that. The West Coast and Texas are in a major drought situation. Of course, Evapco is, we use a lot of water for our makeup per unit, so we're obviously concerned, as the industry at large, not just Evapco. And so what are the water saving potential of a lot of the hybrid technologies out there? And then, we see a lot of advertised water savings from these hybrid designs, but what is the actual water savings you're getting from these technologies? So I want to talk a lot about that. But first, I want to talk about what's the actual water situation, globally. So the population in the U.S. has doubled, but our water usage is tripling. That's a major concern. United Nations projects 15 years. You see most of the population is going to have a water shortage situation. So in the U.S., there are some good news. 10 years, let's say in year 2000, we were using 400 billion gallons of water a day. And now, the latest study is 355 billion. So a lot of our water, saving strategies are working. Most of the water that's being used is in power generation. So 45% of that potable water use is in power plants. And, power plants have cooling towers, so they're using a lot of the water. The real impacts of this water shortage, we see that some of the beef producers are heading north to where the water is, driving their herds up north. California lost 2.2 billion, with their droughts. And locally, I kind of did some research, and Gooding, Idaho is a drought area in Idaho. Has some water restrictions that are taking place, and in the summer, even number of houses can sprinkle on Monday, Wednesday, Friday, and odd number of house numbers the other days. So, in the beer producing industry, very important. They use a lot of water. Okay, right. So you don't want to restrict that. And so Miller Coors 7 years ago, made a goal to reduce 15% to brew a barrel of beer. And so it was 4.1 to 1. Now they're 3.82 to 1. And I think they're improving on that. So their sustainability director made a major statement here: without water, there's no beer. So we need to do something about this. A couple years ago, we found this drought monitor, and this is University of Nebraska, Lincoln, and they put this together, and it's updated. I think it's on actually a weekly basis. This is month-old data. But you can see California, and the dark red there is exceptional drought area, as well as parts of Texas. And you can see it's coming up into Idaho. And projections are not good for the area. It looks like it's going to persist. This is through April 2015, and you may see some more drought conditions. And you can get online and get your region and find out what the water usage and the water drought conditions are. So you can get down to the county level. And so this is Idaho, and you can see in that area, this is Gooding, Idaho, is where the big drought condition is. Looks like that clicked over there, but so in 2 years in Gooding, they're going to have their demand is going to, be greater than their supply. So in reality, water or is going to be scarce. So manufacturers need to look at that. And, you know, you may see people wanting to design around air-cooled systems, but then the air-cooled has it's high horsepower. It takes a lot of plant area. And so the higher energy consumption means more power generation. So then the power plant is just going to shift to the power. So what we need to really look at is the balance of the water, you know, energy-saving technology of evaporative cooled, but mixed with some air-cooled. And that's called hybrid technology. But the first step, you know, reduce your energy consumption. That's your biggest goal for building design, is reduce energy use, and therefore you're going to have a corresponding drop in the water use. And it's a direct correlation: 1% energy drop, 1% water use drop. So let's look at the combination, or you know, the evaporative versus air-cooled. The benefits of evaporative cooling: it's low energy use. You have lower condensing temperatures on your system, gives you overall system energy reduction, and it has a small plant area. But it uses water, it has water treatment. You got to maintain that water. And then depending where you're located, you have an ice management situation. Air-cooled, kind of the opposite. There's no water consumed. It's easier to maintain, no ice management issues, and there's no water treatment. But then you have, you know, 50% more energy, big plant areas, high condensing temperatures, and higher system energy. So it's a trade-off. So you see a lot of equipment being developed that has the combination. This is the hybrid technology. And this is what I'll go over. You have extended surface wetted fin coils. You have these coils in series with an all-dry coil. Or you have a fill section with a dry coil. And this is popular in Europe, an adiabatic pad. It's like a, you know, wetted fill pack on the outside. And then you have a misting where you just spray water in front of a dry coil. And last technology for the power plants is a wet-dry field-erected power plant cooling tower. So looking at the first technology, this is just a bare tube coil that's finned. You can run that wet or dry. So operationally on the left, this is evaporative mode. And then, you know, with that thin coil, you just run the fan, you run it dry, you save water. But it's either wet or dry. So you also have a combination where you put a dry coil in series with that wet coil. You'd run the water through the top section, which gives you some plume abatements. And then, yes? So we can't run any power without letting the fall? Because of the coil made to work better dry? Well, some of the coils that are in series do work better just dry. You just have the fan on, you turn the pump off. So in these, this design can operate dry and meet the load around that 50-degree ambient dry bulb. So compared to a regular wet tower that you're not running the pump, what's the difference? This has well, like maybe the transfer medium called like fill. Of course, it doesn't. You can't with the coil product. You have your capability to run fluid through the coil and run the whole system dry. Now there's a combination has the fill pack, and then it also has a dry coil on top. So this is a closed. This is a closed system. Yes. So the water, the glycol, goes through the coils, and it has its own integrated pump where it's spraying the water on it. And then you have, you know, this design which has a fill pack system in addition to a coil. And, you know, in a wet-dry mode, you have the fill pack in the bottom, which cools the sump water down, sprays it over the coil. So the fluid from the system will go in the top coil there, will be pre-cooled, and then goes into the main coil, which is being cooled by the fill pack. This is, well, it's always a closed system, but it can run dry only where the pump is not on. And I don't know if this has a laser on it, but this pump would be turned off, and you would just run the fan and just bring in air through. This is the air intake here, and bring it out through the top.
So that mixing valve left, top left, is
right.
You want to use the filler.
Well, this actually mixes the how much you want to put through the main coil here versus the dry coil on top. So the pump's either on or off. And there's a comparable design by another manufacturer that actually has the coil in the basin area, and they put the fill on top, so they're cooling the water down and spraying it over the coil, and then they've attached just a little dry fin coil on the outside of the fill pack, so they can run it in different modes. And the water saving capability of these units are maybe not as great, and the dry switchover point not that high. Yeah, both of the systems.
So what's the typical temperature then if you would switch over from dry to wet?
It depends on your application. You may see a 30 to 50 degree dry bulb as kind of an ideal switchover point. A point where if you run wet, you may get ice formation, so you want to try to get it to where, And this is another design where you have adiabatic pads. So these on the outside are wetted. Water just trickles down through these pads, and it reduces the wet bulb, or the dry bulb. I'm sorry. So with this design, you can run water down the left side and have the other side run dry to save even more water. The water is most of it's evaporated before it gets down to the basin. So this is a big water saving design.
But those aren't condenser coils, those are.
This actually is. On the right is a condenser. These are both condensers. And this is a microchannel refrigerant. This is a condenser version. And this could be a cooler or a condenser design. Right now, this is, I think, the only manufacturer that has the microchannel design. There's a design that just mists. It just sprays air out in front of the coil as an operation, evaporates it, but it tends to spray water everywhere, and it's kind of uncontrolled, so we don't really see the use of this. It was brought out in Europe, so they've kind of reduced. You have to treat the water as well, so you don't scale the coils. What is it, just a misting nozzle? Okay. Okay.
Yeah, I think we do.
Okay. Yeah, I think you find the adiabatic is really the best way to go. There's no water treatment required and evaporates almost all the water. The last hybrid design is in the field-erected power plant cooling tower size, and it's a combination of having heat transfer or fill pack in the middle, and on the outside of the tower you have stainless steel fin tubes. And so you can run the water either through the fill pack, through the fin tubes, or a combination of both. They're stainless steel, so you can drain them down, and you have to worry about corrosion. And, if it was a galvanized steel coil, you'd have issues draining the coils out, and they would rust. So you typically would see this in a counterflow design, PVC fill. Some of it would be replaced with a stainless steel tube with fins. So in this design, you have the hot water comes in the header and sprays over the coils, and it sprays over the fill pack. And the coils actually act as kind of like a fill heat transfer. Water runs over and is cooled off. Now, in the wet-dry mode, you just direct that water over the fill pack, and then these run dry, but some of the load is put through these hybrid fin coils. stainless steel coils. So you get your water savings with that kind of design. You also get some plume abatement with that. And the more coils you put in that design, the more water conservation you'll get. And they estimate 20 to 30%. So if we look at all the hybrid technology that we have, and there's various water saving potential. So with the fin tube, you get 20 to 30%. A dry coil with a wetted thin coil in series is over 50%. There's a lot of savings there. The dry coil with wetted fill section, I was not able to find what kind of water saving potential that has. Adiabatic pad design is actually 80%. So something they'd want to think about. I don't see it a lot here in the States. It is very popular in Europe. So we'll probably see more of this adiabatic design here in the States. The missing of the coils is about 80% as well. And you can't see it, but the field directed is 20 to 30%. So that's kind of the published. The manufacturers can give you that estimated water each selection. And selection for the Gooding, Idaho location. ASHRAE, which they focus in the cooling tower power market, is doing a test. Took a little cooler and put it in series with a field-directed cooling tower to see how much water and energy they could save. And this week at CTI, there's a paper being presented on hybrid cooling towers, how much they really save, and how can you measure it. So it has become, a big discussion in the industry. Well, that's right. So you can pick the best one when you advertise it in your marketing brochure. Say you do it in Idaho, it's going to look pretty good. But down in Miami, it might be different, or in Houston. So there's not a benchmark to quantify that, and that's what the CTI is trying to do, try to verify exactly how your water savings is affected by load, by the weather. So, I ran an example. I just, used some software and chose this load, 750 GPM, 30% propylene glycol, and those design temperatures. I used the Burley Municipal, I guess it's an airport, weather data. Used 3 cycles of concentration. I don't know what the water quality is like down there, but hopefully you can get 3. And I selected a commercial HVAC load profile and ran these conditions, and say a basic induced draft kind of closed circuit cooler versus a hybrid. You can see the realized energy savings. So 50% energy savings, 44% water savings. So it does give you some significant water savings. This is the ASHRAE test, where they took a hybrid cooler, have it in series with the cooling tower basin of this field-directed tower. And kind of went over this data, but the power companies know they'll be using a lot of water, so they have to come up with some technology.
So I have a question on that 45%. Is that school facilities, or is that, or are they trying to count all the water that passes through the hydroelectric dam? Is that water usage?
Well, it's, and it's, what's usage too? Like if the river comes through and they cool the steam condensers and it goes back out, is that water usage, or is that borrowed? So I don't know how. There's a study that came up with these numbers. So 45% should be for the steam condensers.
That seems unbelievably high if they're not counting the water that passes through the turbine.
There's a lot. Well, it's a lot of evaporation. There's a lot of water. The cooling towers do use a lot of water. So I don't know if it uses the hydro. Does use a lot of water too, because water is evaporated as the water goes down. It's the waterfall and through the dam.
Like natural.
hydroelectric does, there is a lot of water, and I didn't drill down. There is more in the study about how it's calculated. But that's kind of been the number that's been used for years, around 40%. Right, compared to irrigation and public water supply. Yeah, it is. So this is a Georgia Power. This is their location, and so they looked at a lot of technologies, and they wanted to see how much would a hybrid tower save for energy and water compared to a conventional cooling tower. So this is a dry cooler, dry coil on top, wetted coil on the bottom, using a plate and frame heat exchanger in line with the hyperbolic tower. They ran a 2-day test, 3 different fan speeds, measured all the inlet temperatures, intermediate temperature, and they came up with some graphs, and basically what it showed is that it does save water. You can tell, but this is the orange water saving curve. 100%, 75. I think at each fan speed, the profile pretty much curves look the same. And they saw that during the night is where they had the most water saving, which makes sense that everything's down, wet bulb, dry bulb temperature. And as a result is they're saving 50 to 6%. They realize that much water saving, so it's in line with what you're getting from, the supplier's computer programs and software. You can save water even in the summertime, and for the winter you can have a high switchover point around 50 degrees. So it's a good cooler to use for a lot of applications. And last, there's a paper that's the CTI is presenting, and it talks about the various hybrid cooling tower technology available. And, they promise different water saving potential, but how can you verify it? So there's no method. There isn't a CTI test method for verifying hybrid performance. So this paper proposes to use a benchmark. So of a benchmark cooling tower, same design conditions compared to the hybrid cooling tower under the same design conditions, and show what the water savings is, between the two. So constant heat load, constant hot and cold water temperature, set your guideline, your benchmark. I'm not going to go through all these equations, but enthalpy and humidity ratios. But last part of the paper is measuring the water being used. One method is just measuring the basin water level drop. So at the start of the test, measure the depth of the water in the basin. At the end of the test, measure the delta, and that's the actual water use. I think you could use meters to do this a little more accurately. It wasn't proposed in this paper, but
a lot more accurately. I would encourage this is part of the standard specification.
Absolutely.
We at the university have retrofit those a lot, which is costly.
Sure. The meters can get expensive. And you'll see in 189 that meters are required. Title 24 requires meters on makeup and overflow, so you can accurately measure what's being used. So I don't know either. We looked at it. It's hard to do it, to verify it, to find a meter that will actually work. Yeah, it's open, so at least the makeup coming in is pressurized, and so.
Is the 189 requiring any kind of meter? Can you just have a physical read meter? Or does it need
It needs to be a data collection meter, so you have to be able to have it go into your building system, and so you can remotely tap into it. I think it's both, but you have to be able to have remote data collection, which probably increases the price of the meter, I would think. Yeah. So, like Carlin meter is one meter that we've looked at for, so I don't know, for cooling towers. I think it has a paddle wheel type design. And there's some papers, the water energy nexus is one of the, back up here, one paper that talks about, using evaporative cooling versus dry cooling, how to make that selection, and the EPRI study. So in conclusion, you will have drought conditions continue in the West and in Texas. A lot of hybrid technologies available. Just confirm what your actual water savings are going to be with that design. Try to make sure I would use meters. I think it's easier than working through that CTI paper with the benchmark. So, and that concludes my presentation.
More water savings you have, the more energy you use.
That's true.
I think from your hybrid example, the hybrid has less energy than half is that.
Well, with that,
Including the compressor and all the other that rely on that, or is that just?
that was just on the cooler itself. And one thing I think they found on that design is that the fin coil actually running wet saves energy as well. You get more capacity running wet. Yes?
So, from a cost perspective, what is the selling point? Use less water, that costs the power costs a whole lot more.
Yeah, those coils will cost a lot. So, I mean, that's going to be your payback analysis, expensive upfront cost with that dry cooler, evaporative combination, versus your cost availability of water. Well, we've had some that can be 10 years or some that could be 2 to 3. So, it just depends on how much your water treatment costs. A lot of sewage costs, you're seeing that the sewer costs have been escalating. So you have to include all that as a factor. And we're finding that. What's that?
So you said you saw 10 years on the high end.
Yes. Yeah. That's good. It does. At least it could be 4 months. Some 3 to 4 months. Like December, January, February, you should be able to run dry in all those months. I think you can easily get 4 weeks. Yes. Yeah. If you consider what your water treatment and maintenance and ice management during those months. Yes.
How much does the tower water per year?
Well, I mean, on average, 3 GPM per ton has kind of been the rule of thumb, but that's not, that's 3 GPM per ton. So
That's low.
Yeah. Well, right. So total evaporation, for example, that example there was 1 million gallons in a hybrid, and just an open evaporative was 2 million gallons for a 250-ton application annually. So, cooling towers are definitely being looked at as far as how much water is being used in a building. Yes?
As far as the internal sequencing, obviously, uses dry coil first. But at what point does it decide, okay, I'm going to start using wet coil, and then after that, at what point does it decide to start turning the pump on?
Right. That's a great question, because the control panel, at least with this one manufacturer, has a control sequence to be able to measure the dry bulb outside. And you can preset the set points, and you can adjust it, depending on the load. So those systems should come with a sophisticated control panel to be able to do that.
It's fully adjustable.
It is fully adjustable. Yes. Sure. So does everybody understand that what cycles of concentration are doing the ratio of your recirculated water to your fresh water? So that gives you, so the higher the cycles, you have a 10-cycle tower, you're saving a lot of water. Average 3 to 4 cycles is what you might see in the U.S. So, but you can't just get to 10. You might have a silica issue where if you cycle that high, then you'll have, kind of a glass plating out on your heat exchangers and in your pipework. So you have to look at a lot of the parameters: silica, calcium carbonate, magnesium carbonate, sulfates. Chlorine is also a good measurement. You want to make sure you don't have a high chlorine level, which you might get in a makeup water supply. So I don't know if that answers your question about cycles, but
there's a certain amount of dust associated with that chemical concentration gets high. So you're dumping water and chemicals down and you get a balance.
right. Sometimes programs use conductivity to measure the conductivity that, you have that dissolved mineral content, and they use that as a set point for cycles, not to exceed a certain level of, microsiemens is the typical measurement. So you might see 1,000 microsiemens for conductivity. Okay. Any other questions?
I got one more.
Okay.
You saw first with like lead building where they try to reuse rainwater and flood and stuff like that.
Yes, very popular.
It doesn't work real well around here. We figured out it's such a little amount of rain.
Okay.
And that water is really dirty by the time it does rain. But anyway,
Right.
Have you seen that, that water being used?
Yeah, we've seen that be used, of course. With cooling towers, you have to be careful, though. Got to make sure if you blend that rainwater or other captured water that it meets like a cooling tower manufacturer's guidelines, because you could get too acidic. Air handler condensate is another one that's being used a lot. And in the South, you can capture a lot of water. And so that's actually in 189. So when you have that presentation in May, there's a section in the water efficiency about, certain wet bulbs, you have to use air condensate recapture and use it somewhere.
What is the water quality of condensate?
Well, I think the pH is low. It's pure, but I think the pH is fairly acidic, so it may be detrimental to, to a galvanized steel. If it was stainless steel, it's probably okay, or fiberglass. But, of course, rainwater is acidic as well.
A lot of rhino.
Yeah, I think someone uses that. But, it's we have to look at the chemistry. If you decide, okay, I want to use 20% rainwater or condensate, it has to stay at that volume. And the problem with rainwater, you don't always have that volume. So you have a system that has to keep, measuring the rainwater versus the city water, and then you have to have your valving correct to make sure you have, the right mix.
I know you said 59, but is that condensate capture required in all climates?
It has a climate zone. It says climate zone like 3 through 10, or so they do have it. Like it won't be in Arizona because it's expensive to run all the lines to capture that. So that's a good question. I can answer other 189 questions. Anybody have any questions about that? We're talking about biomass a lot right now. So biomass boilers, and is that a renewable energy source? And so someone wants to add that in there. So we're having a lot of discussion about that. Okay. All right. Thank you.
All right. We're going to continue on.